We start our lection by discipline interchangeability, standardization, and technical measurements. Theme 3. Interchangeability, tolerance and fits of smooth cylindrical joints. Unified system of tolerance and fits, ISO. The plan of our lecture. First item 3.1 size ranges, units of tolerances and international tolerance grades, ISO. 3.2 fundamental deviations, diagrams of the location of the fundamental deviations of the shaft and holes. And 3.3 hole system and shaft system, location scheme of tolerance fields for fits. And we start item 3.1, size, ranges, units of tolerance and international tolerance grades, ISO. The system of tolerance and fits is a set of regularity constructed series of tolerances and fits designed in the forms of standards. Currently, Ukraine has a system of tolerance and fits and the basic norms of interchangeability, which are based on ISO standards and recommendations. Unified system of tolerances and fits ISO extends to sizes up to 10,000 millimeters. ISO International Organization for Standardization. Dimensional accuracy is determined by tolerance. Different in size tolerances for size up to 500 millimeters are found by formula T is equal A multiplied by I, where I is the unit of tolerance, which expresses the dependence of the tolerance on the size in micrometers. I is equal 0.45 multiplied by root of the third degree of d suffix m plus 0.001 multiplied by d suffix m. In this formula, d suffix m is the geometric mean of the limit values of the interval of nominal dimensions. It is calculated by the formula d suffix m is equal square root of d minimum multiplied by d maximum, where d minimum and d maximum are the smallest and largest limit values of the interval of nominal dimensions in millimeters. A. So it was I. I is the unit of tolerance, and A, the number of units of tolerance. In these tables, you can see the numbers of units of tolerance. A, for the IT grade 0,1, A is equal 1. For example, IT grade 3, A is equal 3.7. And for example, for IT grade 14, A is equal 400. Within one IT grade, A is a constant. However, the tolerance in the same IT grade for different sizes change because with increasing size increases the unit of tolerance. In the transition of coarse precision IT grades, the tolerances increase due to increase in the number of tolerance units. In ISO for sizes up to 10,000 millimeters, 19 IT grades are established. In order of decreasing accuracy, IT grades tolerances are conditionally indicated IT01, IT0, etc., and IT17. International tolerance grades, it's IT grades. IT, it's international tolerance grades. So you can see the line of these IT grades from IT01, IT0, IT1, IT2, and to IT17. These are the standard tolerance grades. These tolerance values will be calculated with the help of the relevant magnitude given below. IT grade 01 to IT grade 4 for the production of gauges, plug gauges, measuring instruments. From IT grade 5 to IT grade 7 for fits in precision engineering applications. From IT grade 8 to IT grade 11 for general engineering. From IT grade 12 to IT grade 14 for sheet metal working of press working. And from IT grade 15 to IT grade 16 for processes like casting, general cutting work. There is a table, fundamental tolerances for grades IT01 to from IT01 to IT16. For example, calculate the standard tolerance value. Question: calculate the value of standard tolerance IT grade 7 of diameter 100 millimeters of the shaft. Answer: step 1, calculate the geometrical mean. D. The shaft diameter 100 lies in the nominal size range from 8 to 120 millimeters. And the geometric means D is equal square root of 80 multiplied by 120. And it's equal 98 millimeters. Step 2, calculate standard tolerance factor. We use the formula 0.45 root of the third degree of D, and D is equal 98, plus 0.001 multiplied by D, and D is equal 98. And we have it's equal 2.172 micrometers. And step 3, calculate the value of tolerance IT7. For IT7, A is equal 16. Let's look our table in previous slides. IT grade 7. IT grade 7. IT grade 7. Here you are. and A is equal 16. So IT grade 7 is equal 16 multiplied by I, and we have 16 multiplied by 2.172, and we have 35 micrometers. It's IT grade 7 for value of standard tolerance IT7 for diameter 100 millimeter of the shaft. And now we start item of our lecture 3.2, fundamentals deviations, diagrams of the location of the fundamental deviations of the shaft and holes. A number of tolerances of 19 IT grades and 28 fundamental deviations of the tolerance fields of shaft and holes have been established for the formation of tolerance fields for each interval of nominal dimensions. The fundamental deviations are denoted by one or two letters of the Latin alphabet. You can see it's A, B, C, C, D, D, E, F, F, G. For hole, we use big letters, and for shaft, we use small letters. Fundamental deviation letters for holes, basis H, and fundamental deviation letters for shafts, small h. We use small letters. Fundamental deviations. The fundamental deviation is that limit deviation which defines that limit of size which is nearest to the nominal size. Nominal size corresponds to the zero line. The fundamental deviations are identified and controlled by upper case letters for holes from A to ZC. Holes deviations A, B, C, D, you can see the letters. All letters are big. Lower case letters for shafts. Lower case letters for shafts from A to ZC. Shafts A, B, C, D, but letters are small. And you can see on this scheme the tolerance fields and its fundamental deviations for the shaft and for the hole.
Hello friends, today we will learn deviation, lower deviation, upper deviation and fundamental deviation. Lower deviation and upper deviation. Deviation means the amount by which the dimension goes away from the zero line. Now in this figure you can see zero line, lower limit and upper limit, which we have studied in previous video. Lower deviation. The amount by which lower limit deviates from zero line is known as lower deviation. And upper deviation, the amount by which upper limit deviates from zero line is known as upper deviation. Fundamental deviation. It is either upper deviation or lower deviation, which is conventionally chosen to define the position of tolerance zone in relation to the zero line. It defines location of tolerance zone with respect to the zero line. Suppose, as shown in figure, upper deviation chosen as fundamental deviation, then its position will not change with respect to the zero line. Case 1. To increase the tolerance zone, only lower deviation will be allowed to move down in order to increase tolerance zone. Case 2. To decrease the tolerance zone, only lower deviation will be allowed to move up in order to decrease tolerance zone. So you can see in this figure, upper deviation is constant in both the cases. but lower deviation is varying as per requirement. So, position of fundamental deviation is fixed with respect to the zero line in both the cases. Types of fundamental deviation. There are 25 types of fundamental deviation, and these are indicated by letter symbols. Fundamental deviations for holes. These are represented by the capital letters. And excluded letters are I, L, O, Q and W. Fundamental deviation for shafts are represented by small case letters, and excluded letters are again I, L, O, Q and W. We will learn this topic in detail with IS system of limits and fits. If you like this video, don't forget to hit like button and subscribe the video. Thank you.
The fundamental deviations of the holes should allow the formation of fits in the hole system and in the shaft system with equal clearances and interferences. To do this, there are two rules for calculating the deviations of the holes, general and special. According to the general rule, the fundamental deviations of the holes are taken equal in absolute value and opposite in sign to the fundamental deviations of the shafts, denoted by the same letters for holes with the fundamental deviations from A to H. Big EE is equal minus small es. For holes with the fundamental deviations from I to ZC, big ES is equal minus small e. In exception to this rule is made for deviations of holes larger than 3 mm, J, K, M, and N, with tolerance to IT grade 8, inclusive in deviations from P to ZC to IT grade 7 inclusive. A special rule has been established for them, and big ES is equal minus small e plus delta, where delta is equal IT grade suffix n minus IT grade suffix n minus 1. The difference between the tolerance of the considered IT grades and the tolerance of the nearest accurate IT grades. And rules for fundamental deviations for holes. You can see general rule and special rule.
I've wanted to make this video for a while. It's on something I've found very useful over the years, and I hope you will too. The ISO system of limits and fits. Contrary to most of the other videos on the topic, I'll be presenting this with a working microphone. If you've seen as many videos online as I have about this, you'll get that joke. Before I get too far into this, I want to say that this is my understanding of the ISO limits and fit system, and I did do my due diligence to make sure it was correct, but if I make a mistake, please let me know in the comments so I can either add edits to the description, or if I'm way off base, remake the video. So starting off, any dimension in existence has some tolerance to it. The tolerance specifies how much higher or lower a dimension can be from nominal and still be acceptable. The space between the upper and lower limit is often called the tolerance zone. Think about it like football uprights. Each upright represents a limit, upper or lower. To score a field goal, we kick the ball towards the center, but no matter how the ball flies, as long as it ends up between the uprights, it's acceptable, and our parents will still love us. Before we get any further, I should mention that I'll be talking about shafts and pins fitting in holes, but per ISO 286, this system can be used for internal and external features of size. You'll sometimes see it used for keys fitting in keyways, for example. How things fit together is determined by how much free space there is between the two parts. If there's lots, there will be lots of space for the parts to move. If there's only a little, there will be a lot less space. Finally, if there's no space, the part won't be able to move. In this video, I'll show the hole tolerance zone as red, and the shaft tolerance zone is green. This means that, without measuring, the actual outer diameter of the shaft will end up somewhere in the green zone, and the actual diameter of the hole will end up somewhere in the red zone. A pin can fit into a hole one of three different ways: clearance, transition, and interference. A clearance fit means that there will always be space between the two parts, no matter how the tolerances turn out. Transition fit means there's sometimes space between the parts and sometimes there isn't, but it's usually pretty close. Interference fits never have space between the parts, and one part always has to be forced into the other. It turns out these categories can actually be quite broad. For example, a 9mm pin fitting into a 10mm hole is a clearance fit, but it would be extremely loose. A 9.98mm pin in a 10mm hole is also a clearance fit, but it's much tighter. The former might be good just to make sure two parts don't hit each other, and the latter might be good for making sure the pin stays approximately in the same position relative to the hole. Different fits, as well as their descriptions, can be found by looking up preferred fits and tolerances in the machiner's handbook. There is a preferred fit for most situations, and this is a really good starting point. Also check out the YouTube video by Tarka on the ANSI system of fits and tolerances. The designations are different, but the concepts and considerations are the same. So if we want a dowel pin to fit loosely in a hole, we measure it, we ream the hole to have a little extra space in it, and we put it in. The problem arises when you have a bag of 100 dowel pins and you have to ream 100 holes. Dowel pins have a tolerance on them, and their sizes will always vary a bit. Your reamer will also cut slightly different sized holes, depending on your work holding, wear in the reamer, and the cutting parameters, all of which can change while reaming your 100 holes. Because you bought the dowel pins and have no control over their tolerance, this is called a shaft basis fit. So the challenge is now to decide what size reamer to use to make sure that all the dowel pins fit properly. If you know the tolerance range you can expect from your reamer, and you know the tolerances of the dowel pins, you can choose a reamer size where the smallest hole the reamer can cut still has space for the largest dowel pin. This is called the allowance, and is typically something you choose. You are allowing, say, 25 microns of space between the largest dowel pin and the smallest reamed hole. Because there will be other smaller pins and your reamer will sometimes cut larger holes, you may also find yourself cutting the largest possible hole for the smallest possible pin. The extra space on top of the allowance is called the clearance. If the clearance is too large, the fit might not work. The only way to change the clearance without changing the allowance is to tighten up your tolerance zones, either by changing your manufacturing methods or buying tighter tolerance pins. Conveying tolerance zones can be a bit annoying. Say you own a factory that makes dowel pins. You want to be able to tell customers what the tolerance zone is on each size of dowel pin, but it would be cumbersome to have to create engineering drawings for each size. So instead, you can just say the tolerance will always be a bit over the specified dimension, where a bit over scales roughly proportionally to the target size. We could say that all the pins will be between 0.1 and 0.3% larger than the nominal dimension. The problem is we don't want people to have to constantly calculate what these percentages are. The system we use instead is called the ISO 286-2 standard. ISO 286-2 uses numbers and letters to convey tolerance zones, things like M6 and H7. The number, also known as the International Tolerance Grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest a shaft can be is the nominal size, and it can only be smaller. The H tolerance zone is important because it's taken as the middle. Shafts or pins with tolerance zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerance zones, such as J and JS, where the shafts can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger and the holes will get smaller and smaller. Holes always get an uppercase letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerance zones. For a given fit, we will usually have one component driving the other one's required tolerance zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it was a shaft basis fit. If we're designing a shaft that has to fit in a purchased bushing, we can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H tolerance zone, respectively, since the H tolerance zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerance zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and could perhaps be used to locate parts while remaining removable. The JS7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels in my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerance zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerance zone, but it's also in the H6, H5, and JS5 tolerance zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerance zone before it's cut. The fits also have some range to them. For example, these 3 holes are in the H7 tolerance zone, and these are 3 H6 dowels. Note how they fall through the holes at different speeds due to the minute differences in the clearance. The numbers themselves are actually determined by the IT system, the International Tolerance System. Every manufacturing process can be statistically analyzed and an IT number can be determined. This means that if I'm reaming a hole, I can look up the reaming process and see that at best I can achieve about an IT7. So I can't specify an H5 or a G5 hole if it's going to be reamed. Likewise, if you have to design something to fit inside a drilled hole, even if you don't have the tolerance for the hole in front of you, you can look up drilling and see that it has at best about IT10. So the whole basis for the fit is going to be around H10. So why would you use this system? Personally, I like how much information is available through just 2 digits. If I have to make a bearing seat on a shaft for an 8mm bearing, I can simply look up what tolerance is required from Machiner's Handbook or something similar. If I need a bearing seat for an 8mm bearing on a shaft that will see reasonably high loads, I can see that it recommends a JS5 fit. The machinists are not going to be happy about that. I know from the fact that it's JS it'll probably be a transition fit and might need a little force to install, and the 5 tells me I'll need an IT5 process to make it, which will either involve very accurate turning or cylindrical grinding. As another example, if I want a nice sliding fit and the shaft I require will be in the H6 tolerance zone, I can simply specify a G7 on the hole tolerance without having to estimate how much allowance or clearance I want. Specifying a tolerance zone like this on a drawing does mean that the machinist might have to look up the actual numbers, so typically I include the fit as well as the tolerances. So, knowing the different tolerance zones and having a list of a dozen or so preferred fits, we should be able to design parts that fit together how we want. We also have a means of vaguely checking if a manufacturing method will be capable of hitting those tolerances. In addition to the oft-used pin and hole example, the system can be used for internal and external parallel faces, such as keys and keyways, or other features of size. Well, that was a bit of a dry one, but hopefully you found it useful. If you find any mistakes, let me know in the comments so I can correct them. Thanks a lot for watching.
Fits of all 3 groups. Now we start next item of our lecture. Hole system and shaft system. Location scheme of tolerance fields for fits. Fits of all 3 groups with different clearances and interferences can be obtained by changing the position of the tolerance fields of the 2 parts being connected. However, it is more convenient in technological and operational terms to obtain a variety of fits by changing the position of the tolerance field of only the shaft or only the hole. The part in which the tolerance field is not allowed to fall due to type of fit is called the main part of the system. In ISO, the main parts are holes of shafts with a fundamental deviation of 0. Types of fit. There are 2 basic systems for given tolerance. The hole-based system and the shaft-based system. The main part is the part whose tolerance field is the basis for the formation of fits. Fits in the whole system are fits in which clearances and interferences are formed by changing the limiting dimensions of the shaft. You can see it in figure 3.2. A. Fits in the shaft system are fits is which the necessary clearances and interferences are formed by changing the limiting dimensions of the hole. You can see it in figure 3.2b. The hole base system. Hole basis, lower deviation is 0 and fundamental deviation is big H. And you can see first variant of the shaft, second variant of the shaft, and third variant of the shaft. You can see there are clearance in the fit. There are clearance is equal 0. And there are interference in the fit. The shaft base system. Shaft basis upper deviation is 0 and fundamental deviation is small h. Base size of shaft, and you can see 3 types of fits. Fits with the clearance, transition fit, and fit with interference.
Previously on Mech Minutes Shafting Series, we covered primary considerations when selecting material and surface treatments. All past videos are posted for your reference to get caught up to this week's episode of Tolerances and Fits. A tolerance is the allowable amount of variation from a specified dimension. When tolerances are combined between a shaft and bore, they can be classified into 3 categories known as fits. The clearance fit, interference fit, and transition fit can either assist in assembly or prevent them from being disassembled easily. A clearance fit ensures a shaft can be freely inserted into the intended bore. This generally means the maximum limit of the shaft is less than the minimum limit of the bore diameter. An interference fit guarantees the shaft and bore will interfere at every point within their tolerance zone. This is commonly referred to as a press fit. Often the 2 components must be joined by excessive force, or by altering the atmospheric temperature to slightly expand or shrink the diameter for assembly. The transition fit is a combination between the clearance and interference fit. Depending on the actual dimension of the shaft and bore, it is possible that either could occur. This fit is best used when a shaft must be held in a precise location. If interference should occur, it will not be to the extent where disassembly is overly difficult. Masumi shafts and bores follow the JIS shaft fit tolerances. Selecting the proper tolerance is critical to achieve the desired fit between 2 mating components. This tolerance table can be found in the technical reference section in each catalog. The columns represent the tolerance grade, while the rows are organized by diameter ranges. Finding where the 2 intersect will indicate the corresponding tolerance range. If we look at a 10mm shaft with an H6 tolerance, 10H6, we can see the expected tolerance is no larger than the basic size, but is capable of being 11 microns under 10mm. This brings the expected minimum to 9.989 and the maximum to 10.000 millimeters. Masumi offers a useful table to help you choose the appropriate tolerance combination in your application. If we would like this 10H6 shaft to exhibit a clearance fit, we can see each tolerance class that would satisfy this condition. Now that we're familiar with shaft selection, join us for the next episode, where we will take a look at linear shaft applications and related alterations.
Limit deviations are assigned to all dimensions indicated on the working drawings. The accuracy of smooth elements for which deviations are specified by a common record is normalized either by IT grades from IT12 to IT17 for sizes from 1 to 10,000 millimeters, or by accuracy classes: accurate, medium, rogue, and very rogue, denoted by the letter small t. Accuracy classes are conditionally named and denoted: accurate T1, medium T2, rogue T3, and very rogue T4. In the listed accuracy classes, the limit deviations are set for the enlarged intervals from 6 to 30, from 30 to 120, and obtained by rounding of the average tolerance calculated according to the tolerance adopted respectively in IT grades 12, 14, 16, and 17 for the size intervals included in this enlarged interval. For the sizes of the metal details processed by cutting, IT grade 14 and accuracy class T2 are preferred. There you can see maximum hole size, basic size, upper deviations of the shaft and of the hole. And in figure 3.3, you can see designation of limit deviations and fits in the drawings. 3 types of designation of limit deviations and fits. First type with fundamental deviation, IT grade, and upper limit deviation and lower limit deviation. Second type, only nominal diameter and upper limit deviation and lower limit deviation of the shaft. And third variant, only nominal diameter and only fundamental deviation and IT grades. The same types for the whole too. The same designation of limit deviation and fits in the drawings.
Hole basis system. In this video, we are going to see about hole basis system. The different types of pits are obtained by associating shafts of varying limit dimensions with a single hole whose lower deviation is 0. Consider a basic hole. Clearance shaft. Clearance fit. Basic size. Clearance 0 line. Tolerance zone of hole. Tolerance zone of shaft. When the lower deviation of the hole is 0, the minimum limit of the hole will be equal to its basic size, which is taken as the base for computing all the other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit, basic size, interference fit. Basic size, zero line. Interference or negative clearance. Tolerance zone of shaft. Tolerance zone of hole. Forces required to insert the shaft. Shaft basis system. In this video, we are going to see about shaft basis system. In this system, the different types of fits are obtained by associating holes of varying limit dimensions with a single shaft whose upper deviation is 0. Consider a clearance hole. Basic shaft, clearance fit. Basic size, clearance, 0 line, tolerance zone of hole, tolerance zone of shaft. When the upper deviation of the shaft is 0, the maximum limit of the shaft will be equal to its basic size, which is taken as the base for computing all other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit, interference hole, basic shaft, forces required to insert the shaft, basic size, 0 line, interference or negative clearance, tolerance zone of shaft, tolerance zone of hole.
Okay, our lecture is finished. Thank you very much. Goodbye. See you next time.